So we'll find our first derivative, and what do you get, Morgan? Perfect. So there's our first derivative. We then need to find our second derivative. What is that, Elise? 6x minus 6. Good. And this tells us to determine where the second derivative equals 0. So we add 6 to both sides, divide by 6, and we find out that this is happening at x equals 1. So something crucial is happening at 1 on the original function. We just have to kind of take a look and try to figure out what that is. So I'm going to throw this on my calculator so that we can take a stab at what's happening at 1. And this isn't the best graph, so I'm going to, well, just because I don't have a great window, I'm going to move my window from negative 20 to 20 and hope that does the trick. Nope. Negative 40 to 40. Good. Okay. So what is happening at 1? What'd you say? I don't think it is exactly, no. Oh, it is. It is. That's kind of coincidental. What if I'm going to change that then. What if this was plus 20? That's not going to change the first derivative, is it? So I'm just going to, it's just going to push the, what was that? It was a 15, so I just added 5 more to it. So I'll change my original graph then so that that won't happen. It's really just going to shift it up 5 more units so that that won't be a 0 anymore. But something important is happening at 1. What do you notice about, oh, I don't know. Aaron. Correct. Hence the title. But what does that mean? And kind of in light of what we just did with those tables, which is why I wanted to go over those tables again, is your slope becomes negative. It becomes more negative. It becomes more negative. It becomes more negative. And what happens is, this is like the most extreme negative that it ever becomes. And then so let's say it's a slope of negative 1, a slope of negative 2 here, a slope of negative 3 here, and then a slope of negative 2 a little bit later. So this is the most extreme negative slope it ever reaches. And hence it's created this point of concavity, where prior to that point, it clearly is a part of a graph that's concave down. And then after that graph, you kind of get, not necessarily the halfway point, but you get to a position where, okay, now we're kind of bending back outwards, and now we're a part of a graph that's concave up. But what really is happening is we're reaching our maximum negative slope here. So let's say it's a slope of negative 3, and then your slope is still negative, but now not as extreme, negative 2, and then not as extreme, but still negative, slope of negative 1, until you get back to a 0 slope again. Does this make sense? Okay? So when you have the second, when you find the second derivative in the location at which it's 0, that is when the kind of the severity of the slope turns around. And you reach that negative 3, and then that turns around and it starts to get closer to 0 again. So we have a point of concavity at 1 comma, and we'll use this rewritten version, 1 comma, if you plug in 1, we get 1 minus 3 is negative 2, negative 2 minus 13 is negative 15, Negative 15 plus 20 is 5. So that point of concavity is at 1, 5. Now, I'm going to set up a number line. I'm kind of going ahead a little bit, but as long as we're sticking with this example, I want to give you what's going on here, okay? If I kind of use that interval concept again, and I test numbers to the left of that cutoff and to the right of that cutoff, remember this is where the second derivative equals 0. So prior to this, if I plug in a number less than 1 into the second derivative, do I get a positive or a negative if I plug in 0 here? A negative. So f double prime is a negative here. If I plug in a 2, what's f double prime out this way? Positive. Now what that means is not that our slope is negative before and our slope is positive after, because that's clearly a lie, right? Our slope is negative before and our slope is still negative after. It's not, that would be a first derivative test. When you're testing in the first derivative, you're testing for what the slope is prior. So you could see if I plugged in 0 to the first derivative, my slope would be negative. If I plugged in 2 to the first derivative, my slope would still be negative. When you're testing in the second derivative, you're not testing for slope. You're testing for concavity. So what this negative prior to 1 indicates is that prior to 1, this is concave down, hence the negative. After 1, the graph is concave up, hence the positive. Does that make sense? Okay? So concave down is what a negative second derivative means, and concave up is what a positive second derivative tells you. So kind of in summary, and this is something that I would put on a sheet like this, is that your first derivative test, you don't need to write this, or you can write it on your note sheet if you want, but a first derivative test tells you if f prime of x is greater than 0, then the graph is increasing. Obviously, if f prime of x is less than 0, it's decreasing. That's your first derivative, tells you about slope. Your second derivative, tells you about concavity. So if f double prime of x is positive, we're concave up. And if f double prime of x is negative, we're concave down. Okay? And again, I like to put those side by side because both of them involve this number line and testing points. And again, if you're testing points in the first derivative, you're testing for increasing and decreasing, and therefore relative maxes and mins. If you are plugging into the second derivative, you're testing for concave up and concave down, and therefore you're testing for points of concavity. Does that all make sense? Any questions on that? Okay, so down here at the bottom, a point of inflection is a point at which the tangent line exists and the concavity changes from plus to minus or vice versa. So that's like a point of concavity. Point of inflection is really the term for that, right? Where your concavity shifts. So this right here is a point of inflection because it's changing from negative to positive. This is just kind of a fine print detail. The tangent line has to exist there, and obviously we can look at one, our tangent line exists. Does that make sense? I don't know if we'll come across one where the tangent line doesn't exist there, so we would not consider it a point of inflection, but let's be on the lookout for that. On the next example at the bottom, because that just repeated what I just talked about, determine the points of inflection. So you see point of inflection, you think second derivative. and discuss the concavity of the graph. So there's your number line test. So when we go to do this first derivative, how do we want to handle it? Product rule or distribute first is definitely going to be easier. So before we jump into any derivative, I would distribute x to the fourth minus 4x cubed. So real simple now, our first derivative is 4x cubed minus 12x squared. And our second derivative is 12x squared minus 24x. Set that equal to 0 and solve. How am I going to solve that, Sam? What method? Dan? I don't want to hear it out of you. Sam? Quadratics, we never get, we like quadratics equal to 0. That's a quadratic, correct? X squared? We like quadratics equal to 0. We don't want to add 24x and then have them on different sides. So we either factoring formula, completing the square, you name it. But GCF is probably the easiest here. Pull out a 12x. And then we have 2 potential points of inflection. So when we set up our number line, that's going to create multiple intervals for us to have to check inside of. And we are plugging these into the second derivative. And again, we don't care about value, we just care about positive, negative. So f double prime of negative 1, let's say. What is that? Gives us a negative times a, if I'm plugging in negative 1, a negative times a, why the crickets? Because the points of potential inflection have created intervals for us. We have to pick a point within each interval to check the concavity there. So at negative 1, we plug in a negative 1, and we get a negative times a negative, which is a positive. So we're concave up in that interval. If we plug in 1, so f double prime of 1, I get a positive times a negative, which is a negative. And then at 2, or beyond 2 rather, at 3, plug in 3, I'm going to get a positive times a positive, which is a positive. So when they say discuss the concavity, first of all, the points of inflection, there is a transition from plus to minus and then minus to plus. So your points of concavity are 0 comma something and 2 comma something. Where do we plug in the 0 and the 2 to get the other coordinate of the point? Original, which I'm going to go into this version of the original. 0 times negative 4 will be 0, so that's at 0, 0. And 2 would give me an 8 times a negative 2, which would be negative 16. So prior to 0, so I'll give the intervals when it's concave up. It's concave up from negative infinity until 0. And it's again concave up from 2 to infinity. And then it's concave down from 0 to 2. Now, even though we don't have a calculator to check these, we do know something about fourth degree polynomials. Is that correct? Okay. We do know that this function has roots at where and where? Where's our root here? 0. Where's our root here? 4. Because this is a fourth degree polynomial and it's positive, what do we know about the end behavior? Positive on both sides. I don't know if you did triple roots last year with Mrs. Big Eye, did you? Triple roots kind of, if it's ending high, triple roots sort of like wiggle through. and then this one's your single root, and so sure enough, your end behavior is the same on both sides, and you can see it's concave up from negative infinity until 0, at which point the concavity changes, so from 0 to 2, we have concave up, or I'm sorry, concave down, this right here, this little stretch, you with me? And then prior to turning around at 2, we kind of turn back into the concave up. So you have a point of concavity there and there. Concave up, concave down, concave up, the rest of the way. Good? That make sense? I like this stuff. Do you like this stuff? It's better than related rates, maybe. So, okay. This is the second, more on the second derivative test. If the derivative is 0, okay, then we know it has to be probably a max or a min, right? If the derivative is 0, you've got one of two things going on, either that or this, correct? So if your derivative is 0 and your second derivative is positive, if your second derivative is positive, is it concave up or down? Up. So if your second derivative is positive and it's concave up, then this point is a relative what? Minimum. And if your derivative is 0, your first derivative is 0, but your second derivative is negative, aka it's concave down, then it is a relative maximum. We obviously survived finding relative maxes and mins just by doing our number line test on, on the first derivative, but this is just another way that you can tell if something is a relative max or a relative min. You can obviously know that the derivative is 0, but also assess concavity at that point in your second derivative. Just plug that same number into your second derivative, and if it's positive, it's a relative minimum, and if it's negative, it's a relative maximum. Right? Any questions on that? Just another way. So on the next section, just finding all the relative extrema. Ooh, I don't like this one. This might going to take us a while, but we'll get through what we can. So we want to find where the first derivative is 0, because those are our potential moments of relative maxes and mins. And then we're going to evaluate the second derivative as well, and that's going to just tell us max or min. So how do we want to handle this product rule, right? It's really our only good option. We'll call that the first and the second. So our first derivative is the first times the derivative of the second. Derivative of the second technically requires the chain rule, so we multiply by the derivative of what's inside, but that's a 1, so no worries there. First times derivative of the second plus your second times the derivative of your first. Now if I bring that 2 out in front, it's going to become negative 2/8, which is negative 1/4, x plus 2, times the derivative of what's inside of that, which is just 1 again. So if I clean this up first, this is going to become negative 2/8, which is negative 1/4, times x plus 2 squared times x minus 4. And then another negative 1/4 as a coefficient, x plus 2, x minus 4 squared. A problem like this kind of came up on our review sheet. How can we simplify this expression even further? What'd you say? Take out factoring, yeah. Because number 1, they both have a negative 1/4, so that will come out in front for both of them. They both have at least one x plus 2, so that's going to come out in front. And they both have at least one x minus 4, so that's going to come out in front. So what's really left, we've stripped this first term of an x plus 2, so there's just an x plus 2 left, and we stripped it of its x minus 4, so that's gone. We took out the negative 1/4, so that's a plus. And again, we strip this second term of its x plus 2 and one of its x minus 4, so we just have x minus 4. And then this can all be combined. So your first derivative in its best form is right here, 2x minus 2. Oh, that's not the best form, is it? We could also take out a 2, and then again, you're setting this equal to 0 and finding your potential relative min. Okie doke. Your homework is there at the bottom.